Hello, we are Brooke Rainflower, Dylan Kiernan, Joseph Patishi, and Lena Gonzalez. We are going to discuss the smart grid, what it is, why we need it, and how it is being developed. The first power grids were developed at the turn of the 20th century. Originally, it was only feasible to build out these privately owned power grids in the most densely populated metropolitan areas due to the limitations of the technology at the time. However, as the technology improved and regulations moved to allow monopolies for utility companies, power grids were built across the country, connecting every home to the electric grid. Most of this work was completed during the 1930s and 40s as part of the New Deal to recover from the Great Depression. During that time, consumer power demand was extremely low, limited to a few lights and a handful of electronic appliances per home. It was not until the post-war economic boom of the 1950s that the consumer use of electronics really started to grow. During this period, the use of all the electronic appliances we take for granted today really started to explode and has only continued to grow since then. During the 1960s, economies of scale really pushed electronic generation and transmission, and the network was expanded to more than 60,000 circuit miles. Today, we are still using a power distribution grid that was designed and built from the 1930s to the 1970s. You can easily imagine why that could lead to challenges that will need to be overcome as our energy demand continues to grow. The incidence of power outages is growing. It is now normal to hear of rolling blackouts in California or statewide outages in Texas. This is because our aging grid was not designed to handle the stress of our modern usage. Blackouts cost America $150 billion annually. Electric rates are expected to continue to increase, and global climate change demands a response. Currently, our power grid is centralized, meaning power moves in one direction, from generation to consumption. To meet the needs of the future, we must decentralize the grid to allow power to move in both directions. This will allow for consumers to add power to the grid using solar tiles on the roof, as well as allowing for larger transmission back and forth between regions as supply and demand changes, with things like changes in when the sun is shining and where the wind is blowing. In the traditional model, the consumer is a passive participant. At the end of the month, they receive a bill stating how much power was used and how much it cost. In the new system, the consumer can be an active participant by being aware of peak demand periods and cutting back during those times, or investing in solar cells and selling surplus energy back to the grid as part of net metering programs. The traditional grid, an engineering marvel of the 20th century, was designed in such a way that consumers need to report outages for distribution companies to become aware of issues. In the current model, utilities are primarily focused on quickly recovering from power outages and preventing any further damage to equipment. In a smart grid, failures are automatically detected. Power is instantly rerouted through redundant transmission systems, so there is no single source of failure. The system is much more robust and resistant to attacks and natural disasters. So what exactly is the smart grid? The smart grid and the technologies embodied within it are an essential set of investments that will help bring our electric grid into the 21st century using megabytes of data to move megawatts of electricity more efficiently, reliably, and affordably. In the process, our nation's electric system will move from a centralized, producer-controlled network to a less centralized, more consumer interactive model. Far more than smart meters, a fully functioning smart grid will feature sensors throughout the transmission and distribution grid to collect data, real-time two-way communications to move that data, and electricity between utilities and consumers, and the computing power necessary to make that intelligence actionable and transactive. Indeed, only by bringing the tools, techniques, and technologies that enabled the internet to the utility and the electric grid is such a transformation possible.
According to an International Energy Outlook report, global energy demand is expected to rise by 48% by year 2040. The increased electricity demand with higher number of electrical appliances has caused the grid to be overused as well as more fragile. Peak load consumption causes grid instability, increases operational cost of the system, decreases quality of service, and increases demand-supply gap in the electricity market. To tackle these concerns, utilities manage the demand response of connected loads through peak load management. This practice is essential to fill the supply-demand gap in a sustainable manner and improve grid performance and reliability, mitigating problems such as inefficient energy usage, grid instability, and power outages. There are two primary ways to minimize peak load consumption. The first one is reducing power consumption, which requires developing energy efficient appliances. The second method is to modify consumers' energy consumption behavior and shift consumption to off-peak hours to balance the overall load consumption pattern. Examples of peak management schemes are conservation and energy efficiency programs, fuel substitution programs, dynamic pricing programs, and the main advantage of smart grid is that it can improve the utilization efficiency of power system and the power consuming efficiency. It can intelligently integrate the actions of generators and consumers and can deliver electricity which has the advantages of low losses, sufficient capacity, and high quality and coverage area, accessible, reliable, efficient, safe, economic, and sustainable. These efficiencies provide benefits to both consumer and utility. Examples of smart grid efficiencies are improved capacity of renewable energy in the grid through advanced fault management techniques and technologies for intermittent power sources of renewable energy. On the other hand, there's plenty of examples of smart grid efficiencies related to better energy utilization. To list a few, there is improved utilization efficiency of power generation resources through optimization scheduling technologies. There's also reduced line loss through reactive power compensation technologies, which help regulate voltage. There is improved utilization efficiency of electrical equipment by demand response, a market behavior which makes a response to market price or incentive mechanism to change ordinary electric consumption. And last but not least, there is the benefit of improved power consuming efficiency by feeding electricity information back to the electric power users. This in turn creates a smart interaction and results in green energy savings. The grid is typically planned and designed to operate reliably and to be robust under normal operating conditions. However, there are several extreme events, such as hurricanes, cyclonic storms, and attacks by human agents, that inevitably affect grid performance and at times result in loss of service. A resilient grid is one that can recover swiftly after undergoing adverse conditions such as natural calamities and large-scale coordinated cyber attacks. A common technique that is employed to impart resilience to smart grids is to design microgrids that can operate independently of each other, providing a means for efficient recovery from an extreme event-induced failure. Some important concepts of grid resilience are vulnerability of the system, the degree to which it is unable to cope with a certain event, such as security of information flow and exposure of devices to physical tampering, and flexibility and self-healing, which are properties used to characterize the recovery of the system. Resilience analysis includes potential adaptation and recovery strategies along with guidelines for designing resilient grids. The quantitative approach is focused on developing metrics that can be used to quantify the resilience of the grid. These metrics help assess grid architectures and improve response to adverse situations. On the other hand, the qualitative frameworks focus on identifying potential policies for improving the resilience. These involve identifying and defining different components of resilience and developing frameworks that enable a systematic analysis of the property.
As with any technology, smart grid is vulnerable to cyber attacks. The leverage point for a smart grid is a denial of service attack, DOS. The CIA defines a DOS as flooding the targeted host or network with traffic until the target cannot respond or simply crashes, preventing access for legitimate users, end quote. Similarly to a four-lane freeway being bottlenecked into a single lane during rush hour, the servers cannot handle the amount of data traffic and thus the servers bog down. For a smart grid to connect to the distributed architecture systems, the connection must remain stable. Depending on the severity or magnitude of the DOS attack, the Ames Press submitted a publication stating a litany of damages including, quote, immense loss stemming from jamming channels, modifying a MAC address to gain financial systems and network, end quote. Therefore, stopping communication, crippling the smart grid. Potential avenues smart grid engineers can utilize to reduce risk are network intrusion prevention systems, IPS, and network intrusion detection systems, IDS, technologies. The IPS screens the network for potential malicious incidents and logging information of these events. IDS notifies the administrators if a threat is detected, so to slow down or even stop a cyber attack in action. The mechanisms have a potential to produce a model that either learns the normal operations of a system or creates patterns for every abnormal situation. For example, denial of service attacks, DOS, and or a man-in-the-middle attack, which would extinguish a security breach in real time. Within the context of smart grid technology, upgrade costs must be juxtaposed against monetary benefits of the upgrade. In 2011, research projected that upgrading to smart grid would cost, quote, $338 to $476 billion, end quote. Reported power shortages cost between $104 to $164 billion nationwide, with another $15 to $20 billion due to lesser power quality. A 2004 study concluded that $165 billion would be needed to add, quote, intelligent communications to the grid, inserting robotics and automation into the field equipment, end quote. This report also states that $82 to $90 billion will be spent on transmissions, tech, $232 to $339 billion to power storage, and finally $24 to $48 billion on upgrading consumer smart meters. However, the overall benefits will be worth $1.3 to $2 trillion. Energy companies projected that by 2050, electric bills will increase upwards to 400%, but with smart grid, the increase would only be about 50%. Currently, smart grid technology will save the average household $67 a month or $600 a year due to on-site energy storage. In 1 year, there will be $43 billion a year in energy savings, $48 billion in 5 years, $65 billion in 15 years, and $102 billion in 30 years. The energy saved could power the city of Las Vegas 207 times over, a refrigerator for 199 million years, or cool 378 million homes. Furthermore, yields more autonomy over energy costs as it allows the consumer to toggle energy consumption.
Now we will discuss future trends in smart grid technology. The future of the smart grid involves implementing and utilizing renewable and sustainable energy systems based on a layer design, almost like a layer cake. The bottom layer being our smart homes, then up to smart neighborhoods, then up to smart cities, and finally to an interconnected smart world. So the bottom layer is our smart homes. In these homes, our power will be provided by devices such as solar panels and wind turbines, providing the electricity needed to run our devices, our electronics, and to charge batteries for items that need charging, such as our electric vehicles. The smart home will also contain smart meters, that is, a communication gateway between our home and the grid, letting us know how much energy we are consuming, as well as letting grid managers know how much energy they should send down to us. And our smart homes are where we have the idea of net metering, which involves if we have excess electricity generated from our solar panels and wind turbines, we can sell it back to the power company, therefore resulting in a zero energy use situation. We would not have an electric bill. In fact, we might make money from selling our power back to the electric company to share with others. The smart home also involves having a place to charge our electric vehicles. The batteries for the electric vehicles would be charged from the solar panels and wind turbines, and then the charged energy would be placed into our electric vehicle batteries. The next layer is smart neighborhoods. Smart neighborhoods involves all of our homes having renewable and sustainable energy systems such as solar panels and wind turbines, but it also involves peer-to-peer sharing, which is we can share electricity from one home to another. If one home has excess energy, they can share that with another home in the same neighborhood, resulting in a net bill of zero for all the homes in the neighborhood. Also, instead of every home having an electric vehicle charging stations, there will be neighborhood charging stations where some of the excess energy generated from our homes is stored in batteries in a neighborhood charging station that can then charge the batteries in our electric vehicles. The next layer from our smart homes are smart cities, which are cities consisting of neighborhoods and industrial areas, all utilizing smart grid techniques, all involved in sustainable and renewable energy systems, involving everything being monitored. Devices such as city buses will be scheduled due to need observed from the monitoring, as well as energy provision will be sent to buildings, factories, and other such places as observed from monitoring the grid. Our entire world will end up running on the renewable, sustainable, shared energy resources.